Good afternoon, everyone. This afternoon's students. When the organizers of the ICTS program on nuclear interaction and the many-body problem, especially Dr. Majumdar, mentioned to me that they would like to invite Faddeev to participate in this meeting on nuclear physics because it was the 50th anniversary of the Faddeev equation. So I thought it was a great idea to have Faddeev visit TIFR. And I also thought that we can honor Faddeev not only for the Faddeev equation, but also for the many seminal works he has done in the past 50 years. So incidentally, I'd like to mention that he and several members of his Leningrad group had visited TIFR in 1985 in connection with the school on integrated systems, which was organized by Sriram Shastri, who used to be a member of the Department of Theoretical Physics. So it's a great pleasure and honor for us here in TIFR to have Professor Ludwig Faddeev deliver the ICTS Subramanian Chandrasekhar lectures. These lectures are delivered by very distinguished academicians in their areas of expertise. Faddeev is one of the creators of modern mathematical physics. What sense of mathematical physics he is going to tell us about. He is very famous for proposing the quantization of non-abelian gauge theories using path integrals. Here the key question of the path integral measure was solved by Faddeev and Popov. It involves the Faddeev-Popov determinant and also the associated Faddeev bursts. No rods but bursts. This seminal work laid the foundation of path integral quantization of all constraint systems, including quantum gravity and string theory, both of which have local symmetries. The Faddeev-Popov method is also the basis of solid-on quantization. Faddeev has also made seminal contributions to the theory of classical integrable and quantum integrable systems. The paper of Faddeev and Tattajan on the exact integrability and solution of classical sign-Gordon theory was a timely masterpiece, where the associated linear problem was the Dirac equation rather than the Schrödinger equation, which had appeared in earlier works on the inverse scattering method. So I just want to mention that Professor Faddeev will give 2 lectures on integrable systems, Russian style. That's tomorrow, at first one at 10 o'clock and the second one after lunch at 2:15. Over the years, Faddeev and his students developed the subject of the algebraic Bethe ansatz, and their work contained the germ of the notion of quantum groups. Besides his scientific contribution, Faddeev mentored a great school in Leningrad, St. Petersburg now. He has mentored about 25 students, 15 of whom are now professors in various institutions in the United States and Europe. Some of them you already know: Leon Tattajan, Yevgeny Skilyanin, Nikolai Reshitikin, Korepin, Spilnau, Sakishvili, and many others are his students. Faddeev is also a very honored and anointed mathematician and physicist. He is a member of the Russian Academy of Sciences, foreign member of the National Academy of Sciences, USA, foreign member of the Royal Society of London. He was president of the International Mathematical Union from 86 to 90. His major awards include the State Prize of the USSR, the Danny Heinemann Prize in Mathematical Physics of the American Physical Society, the Dirac Medal of ICTP, the Max Planck Medal of the German Physical Society, the State Prize of Russia, the Euler Gold Medal of the Russian Academy, the Golyubov Prize of the Ukrainian Academy, Poincaré Prize of the International Association of Mathematical Physics, the Shaw Prize, and 5 national orders of the USSR and Russia, including the Order of Lenin. So now request Professor M.S. Narasimhan, who is a member of the council of the ICTS to present a token of our appreciation to Professor Faddeev and say a few words.
I'll just add a few more remarks to what Speklov said. I've known Professor Faddeev for many years, from the time we were both associated with the Institute of the International Mathematical Union. He was the president of International Mathematical Union from 86 to 90. When I was the chairman of a commission of IAE, the Commission for Development, so-called Commission for Development, and at that time we worked together. I had also professional contact with many members of the famous Leningrad group of clinical diseases created, and several of them have visited TIFR for long periods also. I believe his early training was in mathematics, and Vladimir was his mathematics course. And his early work was in mathematics, and it has to do with automatic forms on non-arithmetic case, and it used ideas from scattering theory. And he and his group from Leningrad created the important notion of quantum groups, which is playing a very important role in mathematics. So thus the group has had also some significant influence on mathematics. So I'm very happy to be associated with this function, and I look forward to his lectures.
Thank you very much, Professor Wazia. Thank you very much, Professor Siman. I'm very glad to be here, especially because it's connected with the name of Chandrasekhar, great physicist who made very important contribution to theory of gravity, to cosmology, to the notion of black hole, and other things. I recently looked at his biography and found that he got Heinemann Prize a year before him, so we are somehow connected. Anyhow, so what I will do today will be just very general discussion, almost no formulas, on my understanding of what is mathematical physics. I work already 55 years. My first published paper is from 56, when I just was finishing University of Integrated Studies. And then I continued to work until now. I'm writing papers. But in the course of all this activity, I was thinking also what I'm doing, what must my activity, how it must be called. And the only way I found was that this is mathematical physics. On the other hand, of course, this combination of two words, mathematical physics, is understood very differently by different people, in different times, in different places. And so I was to give my own definition, to which I think I came in the middle of my career, so I will postpone my new definition for later and say something about my career. Well, first, still, about mathematical physics in old times. I'm not historian of science, but it seems to me that in the end of 19th century, beginning of 20th century, mathematical physics was somehow equivalent to theoretical physics. And theoretical papers which used formulas were called mathematical physics. And so from archive of Nobel Committee, it's clear that term mathematical physics was legitimate for nomination, because Poincaré was nominated in this way, and even I think that Einstein from time to time was called mathematical physicist. Also, if I'm not wrong, the chair, famous chair in Cambridge is called Chair of Mathematical Physics, this Lucasian chair. Maybe, well. But then after the great progress of theoretical physics in the beginning of 20th century, essentially connected with relativism, introduction of gravity and quantum mechanics, so Einstein and Schrödinger, Heisenberg, Pauli and other people, there was kind of separation. These people decided that theoretical physics is something and mathematics is only auxiliary thing, and we are not to they are just to be called theoretical physicists. And that was, I think it was not nice. And of course, from my young days, I remember some very unpleasant statement that mathematics is something like chess player, so Kapitz and Landau would think that where to put department of mathematics in academy, it's better to put in the department of sports and so on. And clearly, these great people were playing a lot of such words, and so mathematical physics in the time when I was beginning to learn was not very popular. It used usually at that time either to just auxiliary course of mathematics for physicists. So the textbook of Morse and Feshbach, for instance, is something like that. Or in more mathematical circles, it was connected with partial differential equations, the variational principles, proof of uniqueness and existence theorems, and that was already just a part of mathematics in a way. So the classical examples are books of Courant and Hilbert, or many monographs in Russian by Sobolev, by Ladezhinsky, and other people. So when I began my studies, I went to physics department. One of the reasons was that my father was a mathematician, so I didn't want to learn at department he teaches, so I went to physics department. But in Leningrad, which was St. Petersburg at that time was called Leningrad, we had very exceptional situation when mathematical courses were taught by mathematicians who were just members of the group. And I was very lucky to have very good professor, Olga Alexandrovna Ladezhinskaya, woman, so I'm a student of woman. And she was a specialist in partial differential equations. So because of that, well, and then I went to this chair, to the specialty, but this chair was not allowed to give diplomas. And then in the third year, it was changed. Just in the first year when I entered that, it was changed. This chair was allowed to have diploma students, and I was very first diploma student of mathematical physics in St. Petersburg. So that's once more mathematical physics reappeared in my biography. And, but with Ladezhinskaya, it was very interesting. She did not push me into partial differential equations. And the reason was that she was interested in, of course, in contacts with Courant Institute in New York. And at that time, they had famous student of Hilbert, Professor Kurt Friedrichs, who was in particular was specialist not only in partial differential equations, but also was interested in quantum theory. And at that time, he just published, he first lectured in Courant Institute and published a book which was called Mathematical Aspects of Quantum Field Theory. It was in '51. And Ladizhinsky decided to learn this book. So we had a student seminar. We were 5 young people. We were to read the book and relate it to her. I remember it was, she did not learn too much, but I learned. And so that's how I became. I had my dream to work in quantum field theory. At that time, quantum electrodynamics was finally formulated with Schwinger, Feynman, Dyson, and so my colleagues in the group of theoretical physics, there was much bigger group of theoretical physics. They were very doing diagrams, calculating 1 order, 3 orders, loops, and so on. So they were always having the spurs of gamma matrices and such things. And I learned about general structure of quantum fields, mostly on the example of scalar field. But my dream, of course, was to do something in field theory. But I did not want to work on perturbation theory, and so finally I decided that I must postpone quantum field theory to do something more realistic. And this more realistic was also connected with Friedrich's, because in the end of Friedrich's book there was a small chapter on his approach to scattering theory. And I understood quite well what are wave operators, what are scattering operator, and so on. And also, separately, Ladizhinsky gave me to read some works on so-called inverse problem of reconstructing a potential from scattering data. So altogether, defined my interest for the PhD dissertation. And, but of course, scattering theory was mostly two-body scattering. So there's operator H, H naught, interaction V, which somehow doesn't change continuous spectrum, just two-body problem, so to say. So I was to put problems. I was already free. I had my dissertation, so I was to put problems in front of me, which are not solved yet. I decided to two things in scattering theory. First is to do something in three-body, and second is to do something in many-dimensional inverse scattering. I am happy that I succeeded finally in both directions, and so this three-body already mentioned. A paper was published 50 years ago, and then 10 years later I have also done three-dimensional inverse problem. This is my most complicated paper, but it's not too well known. I will not speak about it. Well, anyhow, I finally got the freedom of doing what I want, because I established myself in a way, and I decided to turn to quantum field theory. And then several things happened occasionally. First is that we had in our library the journal Acta Physica Polonica, and I usually looked at many journals. I was reading a lot, and so I opened it, and there was an exposition of Feynman lecture on quantum gravity. Feynman apparently was given problem by Weisskopf, who asked him, can you do by diagram methods, can you do Einstein effects and so on? So Einstein effects is classical, so it's three approximation, and Feynman calculated much more rapidly than anybody else. But then he began to discuss loops, correction with loops, and found some inconsistency. Then, all right, so he was explaining it to the audience of people doing gravitation who were very far from diagrams for quantum field theory, so almost nobody in audience understood him. But there was Stanley Desser there was Bryce DeWitt, who later, of course, understood him quite well. And what Feynman did, he decided so diagram method doesn't, direct, naive method doesn't work, so he calculated a loop from 3 diagrams by means of analyticity. You know, just imaginary part is a tree, and so you reconstruct full loop. And he found that naive answer and his answer are different by some difference, by some term, which looks very much like contribution of scalar particle, but with a wrong sign. And so, well, he said there are some fictitious particles which must be introduced, but that was calculated only in one loop. So that Feynman, physics, and on the same time, well, when I decided to do quantum gravity, quantum field theory, I was looking for examples. Scalar field theory was already out, and electrodynamics was done, so something new. So I decided the only beautiful theory is gravity. I began to read books on gravity and found also quite unexpectedly, just on the street, small, well, how you call it, tables where you sell things, yeah. There was an old second-hand book by Lishnerovitz, which was called Global Theory of Connections. I found it and understood that Young-Mills field is connection. So it's as geometric as gravitational fields. So why not to do Young-Mills field? Young-Mills field was introduced in 1954 in the famous paper of Young and Mills, and I understand how Young was glad to find out that for non-abelian case, the field strength curvature is nonlinear, different from electrodynamics. It's not only just derivative of potential, but derivative potential plus square of potential. This formula for curvature, I'm sure that he was extremely glad to write it down, and so he began to discuss possibility of using this field. But there was an enormous complication. If you quantize this field in the same way as in electrodynamics, you get, well, in SU2 case, you get 3 vector fields, massless vector fields. 2 of them are charged, and they don't exist in the nature. There is no, of course, massless field means long range interaction, and clearly there was only electrodynamic long range interaction. So, nevertheless, and here is the main point, nevertheless Young felt that it's very important. And so he was already quite popular in the United States, young person came from China, very well developing. So he was given talk at the Oppenheimer seminar in Institute for Advanced Studies, and Pauli was in audience. Well, let me say that, of course, non-abelian connections existed in physics much before Young, because if you take a paper of Hermann Weyl or Fock on electron in Dirac field and gravity, they used spin connection, not the Christoffel symbols, but spin connection, and of course they have written curvature in this form, d gamma plus gamma squared, and so on. So all this was known, and Pauli, of course, also knew it. And for Pauli to introduce somehow, also very beautiful wording is in Weil paper of 29, where he said that electrodynamics is a general relativity in the charge space. So he really understood that besides the space-time, there is also charge space, in this case complex plane, the fiber complex plane on which there are charge fields or sections here. That was all clear. But Pauli, as a physicist, knew this drawback. He clearly did not allow himself to write down paper on that subject because there is no in the nature there are no massless charged vector fields. So Pauli sits, Young writes formulas, and Pauli asks question, but what is the mass of your field? Young stopped and said, it's a difficult dynamical problem. Then Pauli says, it's not excuse for you. Young decided, well, shy person, still young Chinese, so he decided to sit down. But then Oppenheimer, with some political correctness, just told Pauli, shut up, and allowed Young to continue. So you see, here is this dilemma. If Pauli, a famous theoretical physicist and censor, very strong censor of science, understands that there is beautiful mathematical construction, but it has no physical sense. It must not be used. And Young, with his feeling of aesthetics, and thinks that it's still very beautiful and will be used somehow. So now we see these two differences, these attitudes, which I now will say. That's one is that of theoretical physics, and another is that of mathematical physics. And this is kind of, on this example, there is this definition. So more definitely, I would say that mathematical physics now, for me, is not that in the sense of Courant and Hilbert. It's not proof of theorems about results which are known by physicists. It's rather use of different intuition of mathematics to do things which are still relevant to physics. In this sense, there is this competition of theoretical physics, theoretical intuition, physical intuition, and mathematical intuition. In my country, the physical intuition was called physical sense. Физический смысл. And of course, another great censor was Landau, and for him, also, if something have no physical sense, it's nonsense. So Landau was very great critics of more mathematical attitudes. And so I just repeat. So my definition is that it's not proof of theorems. I abolished myself of proofs, but it's just development of structures of somehow based on as possible mathematics as high as possible. Well, until now, the question of Pauli is not answered. Of course, we know very important property of Young-Mills, which is called asymptotic freedom, which is connected with dimensional transmutation, which implicitly introduces mass. But it's not done still in, I don't say in mathematical way, but just in the normal way of description of all this procedure. Well, I will once more go somehow aside. So the beauty of Young-Mills field in this sense is the following. For a long time, we were told that quantum field theory is bad because it has infinities. It has divergences. And even Feynman, well, even inventors of renormalization theory, they were still felt themselves not very safe because of those infinities. But in Young-Mills field, infinities are good, they're not bad, because you have dimension transmutation. The quantum Young-Mills theory and classical Young-Mills theory are very different. Classical Young-Mills theory is conformal theory of massless fields, where it's scaled invariance and so on. But because of dimension transmutation, the coupling constant of Young-Mills is traded for mass, for some correlation length, which appears in quantum Young-Mills. In this sense, we can say that
classically, we have a family of Young-Mills theories. This is kind of charge, it's just parameter of this family. But in the quantum case, there's just one theory. Because now the only scale is, the only parameter is scale, which is trivial. So you're just to fix it, and then, so all numbers are the same. So that's just one theory. And we still need a good formulation of it, for that one theory. This point of view is not still very popular, but I will say that my colleagues like Vilchik or Polikov or Chekiev, of course, would agree with me. Other people don't agree with me, but for me, in recent years, it was very important to realize this property. Well, so returning to old years, I read Feynman and Lishnerovitz and decided to work on Young-Mills, and then, of course, I immediately realized what is the difference of non-abelian case and abelian case, namely that in abelian case the gauge group acts linearly, whereas in non-abelian case it acts non-linearly. And so, if I can say, if I have one point of a mu, then gauge transformation give me a plane, somehow super. And here, the gauge orbit, I use this term, which was very foreign to physical language, is non-linear. So the gauge orbits are somehow these curvilinear lines in this space. And when we introduce gauge condition, like Lorentz condition, which is also kind of plane, which must intersect all these gauge orbits. In the Young-Mills case, when it intersects, it has different angles of intersection. And so it was just this simple idea, more geometrical than physical, give you the way to think that angle is determinant, so there must be determinant, and this must be used. So that was somehow my immediate attitude, coming from, well, more mathematical side. And so that's how this idea was realized by Viktor Popov and me in the functional integral formulation. It's strange that Feynman somehow did not use, well, we do know that Feynman diagrams were derived by him from functional integral. And why he did not return from diagrams back to integral, it's not clear. When I met him later, he told me, well, why did I need a thing back for functional integral? But you see, here we have mathematical construction, because, of course, not very rigorous, because nobody knows mathematically what is functional integral. But nevertheless, it works and gave proper rules of quantization of Young-Mills field. Well, so what I want to say is that from time to time, the mathematical beauty, mathematical consistency may come out before real physical use, and this must not be forgotten. So for that I will give you a rather extended citation from Dirac. Dirac, when he have written a paper on magnetic monopole, it was clear to him that it's a very important paper and it will have many consequences, and so he have written a preface, a long preface, where he discussed about this phenomena of use of mathematical in physics. So the steady progress of physics requires for theoretical the steady progress of physics requires for its theoretical formulation in mathematics that gets continuously more advanced. this is only natural and to be expected. What, however, is not expected by scientific workers of last century was the particular form that the line of advancement of mathematics would take. Namely, it was expected that mathematics would get more complicated, but would rest on permanent basis of axioms and definitions. While actually, the modern physical development have required a mathematics that continuously shifts its foundation and gets more abstract. Non-Euclidean geometry and non-commutative algebra, which were at one time considered to be purely fictitious fictions of the mind and pastimes of logical thinkers, have now been found to be very necessary for description of general facts of physical world. I continue, it's a very nice citation. It seems likely that this process of increasing abstraction will continue in the future, and that advance in physics is to be associated with continual modification and generalization of axioms at the base of mathematics rather than with logical development of any one mathematical scheme on fixed foundation. There are at present fundamental problems in theoretical physics awaiting solutions. For instance, the relativistic formulation of quantum mechanics and nature of atomic nuclear, to be followed by more difficult ones such as problem of life. The solution of which problems will presumably require more drastic revision of our fundamental concepts than any have gone before. Quite likely, those changes will be so great that it will be beyond the power of human intelligence to get the necessary new ideas by direct attempts to formulate the experimental data in mathematical terms. The theoretical worker in the future will therefore have to proceed in a more indirect way. The most powerful method of advance can be suggested at present is to employ all the resources of pure mathematics in an attempt to perfect and generalize the mathematical formalisms that form existing basis of theoretical physics, and after each success in this direction, to try to interpret the new mathematical features in terms of physical entities. It was written in the middle of 30s, and until now, I think it's very actual thing. And so this gives us also the shows us the importance of physical intuition. So, well, let me say something, yeah. Well, returning to young Mills, I cannot help speaking about speaking about this. The paper of Victor and me, we were not able to publish it in Russia, in Soviet Union, because of the censorship of Landau. Landau decided that field theory is dead, must be buried. It's written in one of his last papers. And so our main journal, which easily published my three-body paper, would not publish. I even did not try. They would not publish paper on young Mills. Unfortunately, there was the first possibility for us to publish in physics letters. It just appeared, and the paper was to be not more 2 pages in physics letters. So I was writing very condensed, in very condensed way what we have done with Victor, and it appeared just before David has published a 100 pages paper in physics review, where he still pushed the determinant into denominator as a Gaussian integral in the denominator, because he have written Gaussian integral over Bose fields. He did not know Berezin integral, and he did not know. He told me later. He have written me later. If I knew Berezin integral, I would introduce Gauss properly. But fortunately, I already knew Berezin integral. Berezin was nearby, and so we immediately put it there in denominator, and so that's how Gauss really appeared. Gaussian integral over Grassmann variables was put there. So, just general comment, I would say that physics is in a way totalitarian thing, because it has one goal and one direction, and also the gurus, sensors which look at that everything must be done properly. And mathematics, which is, of course, influenced by applications, but on the other hand is rather free, is much more democratic. So we can do whatever we want. And then, fortunately, from time to time, what is done get applications. What I say. Maybe I will illustrate difference of theoretical, of physical and mathematical attitude to concrete problem, referring to our talk of Yefimov today. So you remember that he introduces giant atoms, saying that, all right, so there is very loosely bound state, which is very big, and then third particle somehow is inside of that, and then this produces the effective 1 over r squared potential. I think that this is exposition in the sense of physical sense, exactly. So Landau school is here in the very best way. But I don't know. My belief is that Landau was calculating at nights and then come to a seminar and discuss in these terms his results. So how you did it, I don't know. But the history was that his colleagues in Physical Technical Institute did not understand this. And so he came to me asking, what do I think about this? And, well, I was to realize everything mathematically. So I begin to think what's going on when there is an infinite scattering length, when in the well, the important part of integral equations for three-body is two-body R matrix, T matrix, excuse me. Well, it's a function of k and k prime, and also a function of energy, which has zeros, which has poles when there are bound states. But bound states are negative. The continuous spectrum is positive, so the full complex plane for T is just like that. But then, what happens when scattering length is infinite? It means that one of the bound state comes to the threshold. So let's think that it's the first one. So we have only what we call virtual bound state. Then this function have not pole, but 1 over square root of z singularity with some 4 factors coming there. And so then in the integral equation for three-body scattering, for three-body bound state, for component psi, let's write it, that we have integral operator depending on z, and we need solution of homogeneous equation. And if we introduce eigenvalues of that operator, then lambda of z, it's usually operator with discrete spectrum, integral operator with completely continuous with discrete spectrum. So there are eigenvalues, lambda n of z, and bound states are energy of bound state are such that solution of this equation, lambda n of z equal to 1, because I did not put lambda here. Now, I was telling him, look at that. In the full equation, we have this term and, of course, something else. But this term produces essentially not 6-dimensional, but 3-dimensional equation. So that operator k is equal to k0 plus k1, and k0 is essentially contains this form factor, but you know, there are of course these Jacobi coordinates k and p, and so it is phi of k prime is kernel. Then square root of z, which will give you z minus 3/4 p squared, and then there is green function p squared plus pp prime plus p prime squared minus z. Now phi's at the small k are rather universal thing. We can show that phi squared of 0 is equal to 1 over 2 pi. Nothing, no, for any potential. It's just property of resolvent. So everything is very, and well, why I write it here? Just only, so you look psi in the form phi of k and some h of p, and so on. And for h of p, you will get this 1 over 2 pi, this integral operator. Now, when z equal to 0, you see that you have here homogeneous function of order minus 3. Such integral operator is not completely continuous. It has continuous spectrum. So this means that whereas for non-zero z, it had discrete spectrum, for z equals 0, it has continuous spectrum. So this means that when z goes to 0, then eigenvalues somehow come into this interval, and they intersect 1 many times. And this intersection of 1 just gives us energy of bound states. So I realized it and explained it to him just when we were sitting. And so I say yes. From a mathematical point of view, you are completely correct. And that's also difference of no 1 over r squared. It's just the property of this in the homogeneity of order minus 3. So that's why, in fact, I say, for me, Yefim effect is mostly 3-dimensional. I don't know this dimension 2.7, I don't understand, but this at least is here okay. Well, you have heard from my comments that somehow relation of theoretical physicists and mathematical physicists was not very easy. And in my country, it was connected also with political situation, because there was kind of difficult relations between Landau and Bogolyubov, not between themselves, but between their groups somehow. Clearly, Landau respected Bogolyubov, but he have done one wrong thing. When Bogolyubov came in 1949 to seminar explaining the behavior of dispersion law for Bose-Gas, that it's linear, that this energy of Bose-Gas depends on momentum linearly, Landau didn't believe that derivation. And in the book of Landau-Lifshitz, it's even written that this statement is contradicting some variational calculations and so on. It was only in one edition, so in the next edition it was taken out, but Bogolyubov somehow was not very happy with this. And so then when next time Bogolyubov, after the paper of Bardeen, Cooper, Schrieffer, described his approach, much more fundamental to superconductivity, he was considered by Landau group not very nicely, but that was all time, and the next generation, in the next generation, we were much more friendly. So when Zamolodchikov was writing down isometrics for scattering for Sine Gordon, I asked him how Termratiasyan, his chief, allowed you to do something two-dimensional. He told, well, I did not ask now. And well, in this generation, like, well, from Landau group, like Polyakov, Zamolodchikov, and my pupils, like Takhtajan, Karepin, Sotashvili, and others, now there is a really great friendship. Unfortunately, most of them are abroad now, but nevertheless, we have contacts, and there is much more friendship. Well, of course, string theory changed very much the generation in the United States. So I believe that now when they use algebraic geometry or algebraic topology and number theory, they do much more mathematics than I was doing. But so string theory somehow became part of more mathematical thinking. And this was quite impressive to pure mathematicians, because this classification of four-dimensional manifolds by means of by Donaldson, and then another paper of Witten and Zyberg on these things was very influential. So in the end of 90s, in the Institute for Advanced Studies, they decided to have a special year when physicists will teach mathematicians what do they do. But physicists are in sense of mathematical physicists, of course, because people who are doing the physical problems by means of mathematical methods in string theory. And I was invited, and I came because the Macpherson, who organized it, Macpherson, algebraic geometry, very far from mathematical physics, have written to me what they want. So the goal is to create and convey understanding in terms of congenial to mathematicians of some fundamental notions of physics, such as quantum field theory. The emphasis will be on development of intuition stemming from functional integrals. So that's new type of intuition. And to continue, one way to define goals of the program is by negation. So including certain important subjects commonly pursued by mathematicians whose work is motivated by physics. In this spirit, it's not planned to treat except peripherically the magnificent new application of field theory such as Zyberg-Witten equation to Donaldson theory. Nor is the plan to consider fundamental new construction with the mathematics that were inspired by physics, such as quantum groups or vertex operator algebra. Nor is the aim to discuss how to provide mathematical rigor for physical theories. Rather, the goal is to develop the sort of intuition common among physicists for those who are used to thought process stemming from geometry and algebra. So when I got this letter with this explanation, I decided to go, because for me it was kind of vindication of mathematical physics now in circles of mathematicians. So there are 2 volumes of this school of this year. I had lectured on functional integrals, but I must say that not with a great success, because still people doing geometry and algebra well, looked at me, but somehow I intentionally use language which I use when I speak to physicists, just because the goal was to introduce this type of intuition which is done in this modern mathematical physics. But it did not work too well. When Deline after was speaking about supersymmetry with all this very, very, very abstract way. That was more understandable to them. Well, I think that the last vindication of mathematical physics and this two-dimensional stuff, which we were doing for many years, is new applications of beta ansatz in modern quantum field theory. It's completely unexpected. So for tomorrow, I will give some exposition of history of development of quantum integrable models, but it was done mostly in the framework of solid-state physics, spin chains, and statistical mechanics, and so on. But recently, there appeared 3 completely separate new applications of this theory. One of them is in this Lipatov-Regge scattering, when some scattering amplitudes happen to become just energies of spin chain of some strange spin of spin -1. But anyhow, I was involved in that. I had one paper on that. Then second is much more popular now, the theory of anomalous dimensions of field operators in this famous ideas S5 string theory. And the last one is a paper of Shatashvili and Nekrasov on classification of supersymmetric vacua in n equal 2 for Young-Mills, where n2 means supersymmetry, so that in two-dimensional space-time they were connected with what we call rational field theory, rational integral models. In the case dimension equal 3 with trigonometric, and in dimension equal 4 with elliptic. So all these things really are somehow began to enter into what remained of string theory. So indeed the development, so I think it's very instructive, beginning with spin chains, then to introduction of quantum groups, and then returning back to physics on the next level in the string theory. It's very interesting trajectory. So, well, maybe I'll stop to say general things. And, well, the main conclusion is that mathematical physics has now completely new structure, a new goal, and new way of thinking. And so once more to repeat, it's not proof of theorems, it's rather using mathematical intuition to do things which are still new to physics. Thank you.
Did you take some questions?
Yeah, of course. Why not?
So he will take some questions if you have. Yes.
Could you comment on the interaction with Bogoliubov and what influence he had on you?
Interaction of Bogoliubov with whom?
With you.
Well, there was no essentially interaction. You see, I was very lucky to live in Leningrad, which were far from Moscow when all these things happened. So I was free from such influence from both sides. And well, of course, there are many underwater things, but I will not speak about them.
Looks like it was a brilliant talk. And it was a brilliant talk, and I think let's thank Professor Faddeev and join us for tea outside.